All right, so we're going to talk about the periodic table. Some history. There were several people that are really responsible for the periodic table. Johann Wolfgang Dobereiner sorted elements into groups of 3. John Newlands took elements when he noticed that when they were listed by atomic mass, similar elements were separated by intervals of 8, or you've heard of the octet rule, 8 electrons in the outer shell. Mendeleev separated elements by similar chemical properties, and he left spaces where he thought undiscovered elements would fit. And you've got a picture. Yours is a little bit different than mine, but this is basically Mendeleev's periodic table. So you can see he has lithium, sodium, potassium, rubidium, cesium, all in the same group. He's got a couple others in there too. And then beryllium, calcium, barium, magnesium, all in the same group, and so on and so forth. And I think this is supposed to be strontium. So what he did was put all the information onto cards, and then they dealt out the cards and looked for a pattern. And when he found the pattern, when he arranged them by mass, he found a pattern that repeated, and that's where the term periodic comes from. Periodic simply means a repeating pattern. So, the next question, how is the periodic table arranged? I forgot the last note on there. Glenn Seaborg is responsible for the modern periodic table. And the modern periodic table is organized by the increasing atomic numbers. Okay, Mendeleev's periodic law was organized by mass. All right. Periodic law, when elements are arranged in order of increasing atomic number, there is a periodic pattern in their physical and chemical properties. When we look at the periodic table, we need to understand that a group or family, we're talking about the columns. When we're talking about periods, we're talking about the rows going across. So now, because my notes are crazy, we're going to skip to page, that's not what I wanted. Page 20, which looks like this. Only yours has metals, nonmetals. What we're going to do is we're going to highlight what are metals, what are nonmetals, and what are metalloids. First, you're going to start with the stair-step line. So get a colored pencil out, get yourself situated on page 20, hit pause, and then when everybody's ready, hit go. So you're going to first draw the division between metals and nonmetals. I call this the stair-step line. All right. That is the division between metals and nonmetals. Pick a color. I'm going to pick orange. And we're going to color all the metals. Okay? Do not color hydrogen, but you will color all in the first 2 columns, except for hydrogen. We will color everything in the middle. You can be as neat or messy as you want. Color what we used to call the rare earth elements that are now the actinides and lanthanides. And then you're going to color aluminum, gallium, indium, tin, thallium, and lead. All right. The next we're going to do are the metalloids. Metalloids, we have boron, silicon, germanium, arsenic, antimony, tellurium, bismuth. Those guys probably are actually orange right there, but we don't really know because those don't hang around long to get information about. Then we're going to pick another color and we're going to do our nonmetals. Starting with carbon. And don't forget, come back over here and grab hydrogen. Now let's talk about characteristics. Okay, so we're back to the new note page that you got. Metals are good conductors of heat and electricity. They're shiny. They're ductile, which means they can be pulled into thin wires. And they're malleable. They can be hammered. Some are more malleable than others, some are more ductile than others. So those are very general characteristics, and I'm going to have you add one more in. They form positive ions, which we call cations. Nonmetals are poor conductors of heat and electricity. The ones that are solid are brittle and break easily. Many of them exist as gases, and they form negative ions, which are called anions. Metalloids are metal-like. They have properties of both metals and nonmetals. They are shiny or dull. They a lot of times will conduct heat better than electricity, and they can be ductile and malleable. But they're both, those are the two main important ones. All right, now we're going to go back to your periodic table and go to page 19. Okay. The alkali metals. We're going to start with the alkali metals. So pick a color. Again, do not color in hydrogen. Pick a color. If you want to color the circles instead of the whole box, you can do that. But these are the alkali metals. And we'll talk about their charges in a little bit. Next, we'll do alkaline earth metals. The transition metals we'll color next. Transition metals are the ones that have electrons in the d orbitals, and that gives them the ability to have multiple valences. We'll do the boron family next. Oh, I didn't do yellow. Again, if I'm going too fast, just hit pause. Carbon family. Nitrogen family. The oxygen family is called the chalcogens. The halogens and the noble gases. The lanthanides are the top row of what we used to call the rare earth elements. And the bottom row, we'll do gray, are the actinides. All right. So now we're going to do the happy atom chart, which is on page 15. First, we're going to name our elements again. The first family, except for hydrogen, are called the alkali metals. If we draw a Bohr model of alkali metals, they have one outer shell electron. So their valence shell, valence electrons, are found in the outermost energy level. Okay. All of their electron configurations end in S1. N stands for the period. So lithium ends in 2s1, sodium in 3s1, potassium in 4s1. The next family are the alkaline earth. They have two outer shell electrons. They all end in S2. The third family we're just going to call the boron family. They have three outer shell electrons. They all end Ns2 and P1. Again, N means energy level. That's a quantum number. The next family we're going to call the carbon family. They have 4 electrons, and they all end Ns2 and P2. The nitrogen family, one, two, three, four, 5, Ns2 and P3. The chalcogen family, two, three, four, 5, 6, Ns2 and P4. The halogen family, 7 outer shell electrons, 1, 2, 3, 4, 5, 6, 7. Ns2 and P5, and then the noble gases have 8, 2, 3, 4, 5, 6, 7, 8, Ns2 and P6. All right, looking at the alkali metals, they have 1 outer shell electron. What do they want to do in order to be happy? Because the only truly happy elements are the noble gases. The noble gases have a full octet. They have 8 outer shell electrons. They have full energy levels. Okay, everybody else wants to be just like the noble gases. So what are the alkali metals going to do? Well, they can either lose the 1 electron or they could gain 7. I'm going to tell you right now, it's easier to lose 1. And when they do that, they become positively charged. The alkaline earth, consequently, will lose 2 electrons, and they become a +2 charge. The boron family will lose 3 electrons and become 3+. Carbon's half and half, so he can either lose 4 or gain 4. So he would either have a +4 or a -4 charge. The nitrogen family is going to gain 3. If he's gaining electrons, he's getting more negative. The chalcogen family will gain 2, so he's -2. The halogen family will gain 1, so it's a -1. And these guys are fat and happy, which we had a kid a couple years ago say that means they're fappy. Fat and happy. That's what all the atoms want to do. They want to have 8 outer shell electrons. They can do that by losing or gaining or sharing. This is what I call the happy atom chart. Just like your mole map, this is very important. So you want to hang on to this.